All right, so this video is meant to go over examples of finding intervals of increasing and decreasing for section 3.3. All right, so assuming you've watched the previous video, this is a continuation. This is going to cover some examples. Recall that for all x in the interval open interval a, b, the function is increasing if its first derivative is positive, so greater than 0. The function is decreasing if its first derivative is negative, which is less than 0. So positive, negative, and then it's constant if its first derivative is equal to 0 for all x in the interval AB. So this is a picture, and you'll see that C is a critical number. So I guess right here, the function can switch from increasing to decreasing, or vice versa at critical numbers. And in this picture, so C is a critical number. To the left of C, you have the functions increasing, and its first derivative is positive. So it's increasing, going up from left to right, and then to the right of C, the function is decreasing, and its first derivative is negative. For all of those values on that x values corresponding to that the graph to the right of C. So it's decreasing. Right, so that's important because we're going to use that knowledge to develop a strategy for finding intervals of increasing, decreasing. And here's the strategy. You first find the derivative, and then you find any critical numbers. Then you're going to determine what the intervals are. And for each interval, you're going to pick what's called a test value. And then you're going to use each test value and plug into the derivative. And you're going to make note of the sign. So recall if it's positive, so f prime of x greater than 0, that means the function is increasing. If the sign is negative, so f prime of x less than 0, that means the function is decreasing. All right, so that is the strategy you're going to use to determine these intervals. Okay, so here are two examples I'm going to work out, and we're going to find intervals of increasing, decreasing. So for number 11, I'm going to invoke this strategy. So I need to find the derivative, determine the critical numbers, and then I'll talk about forming the intervals. So number 11. So I need to first find its derivative. So g prime of x. Derivative of x squared is 2x by power rule. And then minus, and then 2 times 1, because the derivative of x is 1, and then 8's a constant, so that would be 0 for its derivative. So the first derivative, g prime of x, is equal to 2x minus 2. All right, and I'm going to actually circle this, because we'll use this later on. Now I'm going to find any critical numbers. So find critical numbers. Well, recall that finding the critical numbers, that's from section 3.1. We determine any cases which the derivative doesn't exist or when its derivative equals 0. Now its derivative is 2x minus 2, that's a polynomial, and polynomials are continuous, which means, and they're differentiable everywhere. So in other words, there's no value x for which its derivative does not exist. It's going to exist everywhere. So we only focus on when it's equal to 0. So set g prime equal to 0. So we have 2x minus 2 equal to 0. All right, and solve for x. So you basically add 2 to both sides. So you have 2x equal to 2. And then divide by 2, so x is 1. All right, so our critical number is 1. And usually they just use the letter C, so I'll use C equals 1. All right, so that's the first two steps in the strategy. Now, the third step is to determine the intervals and pick a test value for each interval. So we base it off our critical number. So we have an interval that's going to be to the left of C, and an interval that's going to be to the right of C. So if you want to draw a number line, say that's 1, that's our critical number, and we have the interval that's to the left of that critical number. That's going to be from -infinity to 1. All right, that's one of the intervals. The other interval to the right of 1, that's all of this. And that's going to be 1 to +infinity. All right, so then you just pick a value from each interval. A convenient value that I would pick from the first interval, -0 or -infinity to 1, would be 0. I'm going to pick the test value, and I'll label it x1 equal to 0 from the interval -infinity to 1. Then I'm going to pick a value to the right of 1. From the second interval, I'll pick 2. So these are just convenient values to pick. I'll use x2 for the second one, and that's going to be equal to 2, and that's from the interval 1 to +infinity. All right, so those are my test values. Now I need to plug them in, so I'm on the fourth step. Plug each test value into its derivative and make note of the sign. So that's why I circled this, because I'm going to be using it now. So g prime of x is 2x minus 2. Now I plug in each test value and record its sign. So if I plug in the first test value, which is 0, that's going to make g prime of 0 equal to 2 times 0 minus 2. All right, so that's 0 minus 2, so that's -2. We don't care what the actual value is, we just need to make note of the sign. So it's negative. If its first derivative, g prime of x, is negative. That means when it's negative, that means the function is decreasing. All right, so it's decreasing. And this came from the interval -infinity to 1. So it's decreasing on -infinity to 1. So then the other test value is 2. Plugging in 2, that's going to be 2 times 2 minus 2. So that's 4 minus 2, which is 2. And again, we don't care what the actual value is, just the sign, and it's positive. And since it's positive, that was using the first derivative, so g prime of x is greater than 0. And when the first derivative is positive, that means the function is increasing. And it's increasing on the interval 1 to infinity, because that's where we picked our test value from. All right, that is the answer. We've determined the intervals of increasing and decreasing. All right, so based on our number line, we determined that for this left, -infinity to 1, it's decreasing. And then from 1 to positive infinity, it's increasing. All right, so I usually just put a sign there to make note of that. All right, so that's it for that one. The next question is number 17. All right, so for number 17, it's y equals x minus 2 cosine x, and it's defined for x between 0 and 2 pi. So if you want to express it, so this is an inequality, you could put it as parentheses 0 and parentheses around 2 pi as its interval. So they specify a domain for this question, whereas the previous question, there was no domain specified. They just gave us the function. So like before, we find its derivative. So find the derivative to y prime. So the derivative of x, that's 1. So that'd be 1 minus, and then you do 2 times the derivative of cosine. The derivative of cosine is negative sine. So y prime is equal to 1 plus 2 sine x. All right, so at this stage, we should be familiar with all of the derivative rules. All right, so the derivative of cosine is sine, negative sine. All right, so that's what we find, the derivative. Now we need to find the critical numbers. Now, sine function is continuous and differentiable everywhere. So there's no cases in which its derivative is not going to exist. So we only focus on when its derivative is equal to 0. So we set y prime equal to 0. So 1 plus 2 sine x equal to 0. So you could subtract 1 from both sides. So you have 2 sine x equal to negative 1. And then divide by 2. So sine of x equal to negative 1/2. All right, so then I ask myself, well, when is the sine function equal to negative 1/2? And I usually reference the unit circle. And if you look at the unit circle, sine is negative 1/2 when x is 7 pi over 6 and 11 pi over 6. And since our domain's restricted between 0 and 2 pi. All right, so these are the critical numbers. So you have C1, I'll call for the first one, 7 pi over 6. And then C2, it's 11 pi over 6. All right, so I found the critical numbers. Now I need to determine the intervals. All right, keep in mind we had the domain they told us was 0 to 2 pi, so keep in mind. They gave us the domain 0 to 2 pi. All right, so that's beneficial for when I form my intervals. And so it's in parentheses, so I'll put parentheses at the end point. So here's 0 and this is 2 pi. So we have about 7 pi over 6 is somewhere. And then we have 11 pi over 6 is somewhere. So what are my intervals? All right, so basically I have this interval going from 0 to 7 pi over 6. Now notice every time I do this, I'm using parentheses around the critical number. So I'll put parentheses around 7 pi over 6, 7 pi over 6. Then I have the interval that's in between the two values. So that's 7 pi over 6 to 11 pi over 6. And then last, I have a third interval going from 11 pi over 6 to 2 pi. All right, those are my intervals, and I need to pick a test value from each interval. So let me list the intervals. Okay, so for the intervals, if I use test values, so this will be test values. So for the first one, if I do a test value in the first interval, well, something that's in between 0 and 7 pi over 6 is pi. So I know pi is in between those two values. So I'll say x1 equal to pi. Now for the second interval, 7 pi over 6 to 11 pi over 6, I know 3 pi over 2 is a value that's in between. So x2, 3 pi over 2. And these are just values I pick, and I know these are values on the unit circle. Now 11 pi over 6 and then 2 pi. There isn't a convenient value in the unit circle that we can use. So what I do is first determine, well, what's 11 pi over 6? So I plug that in the calculator. And let me do that. Eleven pi over 6 is about 5.75 96 if I were to round. So that's rounded. So if I were to pick a value that's more than that, I just go with maybe, let's say 5.8. Again, I'm using a value like 5.8 because 11 pi over 6, if you look at the unit circle, there's no convenient value that's between 11 pi over 6 and 2 pi. And so I first figured out, well, what is 11 pi over 6? And it's 5.7596. So then I just picked 5.8. Okay, so all right, so again, this is just my visual representation. It's not really going to necessarily be accurate as far as the distances go, but visually it helps to see. So these are my test values. Now I need to plug these into the derivative. Into f prime, or really it's y prime. And the derivative is 1 plus 2 times sine x. So if I use the first test value, pi, So that's going to be y prime equal to 1 plus 2 sine of pi. Well, what's sine of pi? So sine of pi is 0. So it's going to be 1 plus 0. So this goes away because sine of pi is 0. So you're left with 1. And the point is that this is positive because you get 1, and that's so that's positive. And so maybe underneath each test value, I'll write the sign. So when we plugged in pi, we got it to be positive, which means since this came from the interval from 0 to 7 pi over 6, that means it's increasing on that interval. So positive, so therefore we know it's increasing on 0 to 7 pi over 6 because our test value came from that interval. At least that's part of the answer. All right, now we do the second test value is 3 pi over 2. So plugging that in, the 1 plus 2 sine x, that's going to be 1 plus 2 times sine of 3 pi over 2. All right, and let's see, what is sine of 3 pi over 2? So sine of 3 pi over 2 is negative 1. So this will be 1 plus 2 times negative 1, which is going to give me negative 1 because it's 1 minus 2. But the point is that's negative. All right, so we know for the second test value that produced a negative number, and that means the graph is decreasing. All right, that was plugging into the derivative to give me a negative number. So this derivative was negative. All right, and so we say this is decreasing. And that came from the interval 7 pi over 6 to 11 pi over 6. All right, and now our last test value is 5.8. Now you notice it alternated from increasing to decreasing. I guess logically, I would assume the next one's going to be increasing since we're dealing with critical numbers, and usually at the critical numbers, it would switch from increasing to decreasing. Now, I wouldn't say that's 100% of the time, so don't just assume that. You need to check that that's the case. So intuitively, I would say the next one's going to be increasing, but we need to check to make sure that intuition's right. So I did 5.8, and that was the third value. So plugging that in the derivative, that's 1 plus 2 sine of 5.8. Make sure your calculator is in radians when you plug that in. Now you'll get this to be approximately 0.071. But the point is that that's a positive number. All right, so the intuition holds. Since it's positive, then yes, it's increasing. And again, so for this one, it was positive. That came from the interval 11 pi over 6 to 2 pi. All right, and that is the answer, just determining the intervals of increasing and decreasing. The next video will cover first derivative test, and honestly the first derivative test covers these same things, and the only added thing we do is check whether it's a relative max or min, which I can give you a preview is that we know for this one, this gave us a positive value for its derivative, so we know the graph will be going up. And then we know from this one it gave us negative for its derivative, so then it'll be going down. So going from increasing to decreasing, that would tell us we would have supposed to have a relative max at 7 pi over 6. And then this last bit, it was increasing because it was a positive value. So we would expect a relative min at 11 pi over 6. So that's really what the first derivative test incorporates, but we'll do specific examples in the next video. All right, that was just a preview. For this one, we just needed these 3 answers, increasing, decreasing, and then increasing for the corresponding intervals.